the Center for International Climate Research in Oslo, Norway. And you heard my colleague Carly Illes yesterday, so we're working together in Cicero. And so I'm putting it in presentation mode. Yeah, so do you see my slides? Yes, perfect. Okay, good. So this lecture will introduce you, or maybe some of you are already familiar with the topic or with some elements of weather and climate extremes, but I will start this lecture with explaining a little bit of what are extreme events, and then I will go into more detail how we define or calculate extreme events based on the extreme value theory or also indices for climate extremes. And then I will show you results or figures from the 5th assessment report of the Intergovernmental Panel on Climate Change that has a lot of information about past, current, and future extreme events. And then I also link to the IPCC risk framing, where climate extremes, of course, play an important role as a hazard driver of risk. Okay, so for those that, of course, work with extreme values already, that they know it, but I start a little bit from the very general side. What is an extreme event? If we look at the dictionary, extreme is associated with reaching a high or to the highest degree, a value, a very great value, or also not usual value, exceptional value, or very severe or serious. And an event is something that we associated with a thing or occasion that happens or takes place, especially one of importance. So how do we translate that in the climate science, weather science? Here we look at extreme events in a more technical sense, the occurrence of a value of a weather variable above or below a threshold near the upper or lower end of the range of its observed value in a specific region. And I will explain this concept a little bit later. It's basically you have a distribution of a climate variable like temperature, precipitation, and you look at the tails of this distribution. And also when you think about distribution, you can think in terms of return periods, an estimate of the average time interval between the occurrence of a particular event of a particular intensity. For instance, 100-year flood. You have most likely heard this terminology before. So here we identify an extreme event by its intensity and how often that occurs in a specific time period. But in general, there is a wide range of extreme events that can have different spatial and temporal scales. For instance, a heavy rainfall event occurs at very localized scale in a very short time, maybe only an hour. And then we have droughts or heat waves that expand over a very large area and that can last for weeks, for instance, or months if you think about a drought. So it's in that sense difficult to have one definition for an extreme event. And also the language used in climate science is not very precise. You find various papers looking at extremes, but characterizing extremes in different ways. For instance, an exceedance over a relative low or high threshold, like the 10th percentile, 90th percentile of daily temperature rainfall, or they just call it rare events in terms of long return periods, 100, 500-year return periods. Or also there are papers that talk about unprecedented events, like record events, like something that has never happened before, like what we have never observed. Then from the historical period, then they characterize that as unprecedented events. And as I said, extreme events can range from very small scales like tornadoes and hailstones to large scales like drought and heat waves, and not only in time, but in space. And one important aspect to consider when thinking about or working with extreme events, it's extremes in one location may be more normal for another location. Like for instance, hot for us in Norway, hot perceived hot summer may be just average or normal in the Mediterranean region. So that is also to consider, and that's why it's hard to have one general definition for extreme events. But I explain the concept also in the context of your location, Novi Sad. I extracted this weather forecast from the Norwegian weather service, called Ør. And this, what you see here is today, it's a pleasant day in Novi Sad, according to the weather forecast, to the high like 16 degrees, and it's becoming even warmer towards the end of the week. And according to the climatology for your location, Novi Sad, in April, you have around the warmest temperatures in the climatology, around 18 degrees, 18 to 19 degrees, and the colder temperatures are around 8 degrees. So this April that you experience right now is more on the warmer end of the temperature distribution for your location. And 18 degrees in Norway is already a very warm April. So so if you think about these range for Novi Sad, and you think about the temperature time series you can collect from the previous 20 or 30 Aprils, then you get this temperature distribution, and you have some Aprils on the cold end, like those that would have been in the 8 degrees maybe, and you have some Aprils like now on the more warmer end, and then you have lots of Aprils in the middle that make the temperature distribution for your location, and then you can specify certain thresholds to describe your extreme Aprils, basically. Okay, but depending on where you live, this distribution is of course different, and we have a wide range of climate zones around the globe, reaching from polar to cold, moderate zone, tropical zone. And we as humans, we have adapted to the different extreme climates there. For instance, in the polar region, for us, very harsh and cold conditions is for them not so extreme. That's what they have adapted. And there's other regions where people live with the conditions of forest, for instance, or savanna, and also in the desert where it's very dry and hot. For our climatology in Europe, but still for them this is not extreme. That is their normal climate. So we have to see the climate extremes relative to the climatological context. Yeah, and here I want to come back to what Manfred Muddelsee in his lecture on workshop day 1 referred to as extreme, just to put it in context to what I'm talking about here. So he used the climate equation, where he said, like, we have a climate variable observed over time, and there could be a trend in that climate variable, and then there's these outliers, and he also referred to that as extremes. And then we have the noise or the climate variability part of it. And there's two ways to interpret an outlier. That I just want to make that point. So it's on the one hand, it could be in the sense of an extreme, as I just explained, that it's in the far tail of the distribution, and that's why it's an outlier, but it still belongs to this distribution. So it's still something that has been observed like the other data points. But there could be also the outlier in the sense that it doesn't belong to distribution because, for instance, the measurement side has been damaged, for instance, or there was an error in the measurement. So outlier could also be something that is something that actually doesn't belong to the time series. There's an error. So, but we are looking at outliers, or when we're thinking about extremes in a time series, it's not an error or something that doesn't belong to this distribution, but it is something that is very on the tails. Outlier is important for observations, for instance. There needs to be a careful quality check. I guess you have heard about that as well, to detect these outliers. But there is often a complication to if you do that automatics, if you make that operational or make it automatic. Sometimes there could be mistakes. If there's a very high extreme event that has never been observed, is it really an outlier or is it an error? So here then we need to be careful. But okay, so today we're focusing basically on the extreme part, and also extremes can have a trend. They are affected by the trend and by the variability, and I will describe now. But also extreme events, if you think about it, when you think about in the societal context, it's not just the statistical properties like the rareness, but also the high impact of it. Like the extreme events, when they hit areas where people live, often cause significant loss of life or damage of property. They are associated with high economic losses. And that you can see in the statistics of the reinsurances that every year provide an overview where the most costly extreme events or the most costly natural hazards have been have occurred, and 90% of all damages are caused usually by weather-related extreme events. It's not so much the volcanoes or other hazards that they also look at, but it's 90% are coming from weather-related extreme events. 90% of the losses. So this is also a significant characteristic of weather extremes, if you think about it. And that's how it is also captured in the IPCC in the context of risk, which I come to later. So extreme events are rare events with high impact. And that the high impact component comes from the part of the society, if it's vulnerable and if it's exposed to the extreme event. Because if an extreme event happens somewhere in the desert where nobody lives, then we don't care so much about it. Okay, and I talked already a little bit about the Intergovernmental Panel on Climate Change. You're probably all familiar with that. The last assessment reports in the 5th assessment cycle came out in 2013 and 14. There are 3 different working groups: the physical basis, working group 1, the impact, adaptation, vulnerability, the working group 2, and the mitigation, the working group 3, working on separate reports, and then they're synthesized in the synthesis report. And this is our main scientific main instrument to inform policy about the current state of the art knowledge of and science of climate change. And in between these cycles, so these main reports come out every 6 or 7 years. We have special reports, and there was a special report in 2012 on managing the risk of extreme events and disasters to advance climate change adaptation. And that was a joint work of the 2 working groups, 1 and 2. But today I'm focusing first on the physical basis. of the changes of climate extremes, which are the combined effects of anthropogenic climate change and natural variability. And in the physical basis assessment, the report 1, or from the working group 1, in the 5th assessment cycle, extremes were covered in several chapters: in the observation chapter, in the model evaluation chapter, in the detection attribution, in the near-term and long-term climate change projections. And if you don't have time to read all these, the whole report, you can read the summary for policymakers of the working group 1 to give you a summary of the findings. But I will show you some of the figures that are shown in the report in this presentation. So coming back to the original distribution or illustration of a perfectly Gaussian distribution for temperature, then this is maybe what we have observed at a place like Novi Sad, and with climate change, this observed distribution, because global temperatures are warming because of the anthropogenic greenhouse gas emissions, this temperature curve shifts to warmer temperature. So we have a shift in the temperature distribution, also characterized by the increase in the mean, which leads to the change in the tails where the extremes sit. So we have less cold extremes and more hot extremes, and also included are those unprecedented, more record hot weather. And the further this curve shifts, the more hot extremes we see. And this is also this is not only we see that in the mean, but there's also changes in the variability in the shape of the curve. So that is not illustrated here, but it's also in this concept that we need to consider. So the problem to now assess or quantify and calculate extreme events is that, as I said already, extreme events are rare in space and time. So that leads to the fact that we have a lack of observational data, because an extreme event doesn't happen every day. It happens once in 100 years, or if you're going less extreme, once in 20 years. So ideally, we would need a long record to really have a good statistic of our extremes. But usually we don't have that. And a lot of areas in the world don't even have long enough observational records, or don't have any observational records of extreme events. So that challenges the analysis of extreme events. And also, as I said, there's no universally valid definition. I mean, there's no one definition for an extreme event. So how do we assess, how do we monitor changes in extreme events if there's not one single definition? And then we have the problem of the mismatch between a point observation, for instance, in rainfall and a rain gauge, and we collect the rain for one specific location, and the model output, which is usually in a grid box, as Carly explained in her lecture, and then so averages over a larger area, like 100 by 100 kilometers. And that causes basically a mismatch in the scale from much higher values we get for an observed, very localized extreme rainfall event and the average over a larger area. So these things we have to keep in mind when looking at comparing observations with models, and when looking into future projections. And the approaches we have taken in the IPCC assessment, or those that are assessed the most in the IPCC report, are on the one hand the indices for climate extremes, such as defined by the expert team on climate change detection and indices, which I explain a bit more in the next slide, and or further on in my presentation, and the extreme value analysis, based on which we can calculate return values or return periods. So these are the main broader categories of how we assess and calculate extreme events. So the difference is basically that the indices are a non-parametric way to quantify extreme events. It's a metrics to count, for instance, absolute occurrence of an extreme or the threshold exceedance of an extreme event. For instance, the number of frost days. There you count when the daily maximum temperature is below 0 degrees, and that counts as a frost day. So within a year, you count how often it's the daily maximum temperature is under 0 degrees, and then you have maybe for Novi 30 days, and then for Oslo you have maybe 100 days a year. Or we have more complex indicators like the Heatwave indicator, where you look at the threshold, for instance, all the days in a location that are above the 90th percentile of the temperature distribution. And if this condition exists for more than 3 days, then it's a heat wave. And then you quantify this heat wave condition with this type of indicator. And on the other side, you have the extreme value distribution, which is a continuous probability distribution, which is parametric. You have certain parameters that describe your distribution, and based on that, you can calculate return values. But these two approaches are not separate; they're complementary. As I will show later, you can of course fit an extreme value distribution to some indices for climate extremes and calculate return values. Okay, so are there any questions for that part? Because now I will jump into explaining a little bit more about extreme value distribution.
So far, there's nothing in the chat, but maybe somebody would like to ask in person. So please just turn your microphone on and ask if you have any questions. No? Nothing yet, so maybe later. Thank you, Jana.
Okay, so the extreme value distribution. So this is based on the extreme value theory, and I cannot go in very much detail, but I will explain. So here we're having our nice Gaussian temperature distribution, and to basically calculate an extreme, we could look at the standard deviation. And we can, for instance, say our hot extremes are starting when above 3 times the standard deviation. So then we have our hot extremes. But actually, for the extreme value statistics, for the extreme events, we are not interested in the full distribution. We are interested in the characteristics of the tail and only the tail. So, so that's why the extreme value distribution or extreme value theory is based on characteristic or describing the distribution only of the tail. For that, we need to sample out of the tail. So we have our distribution of daily values, and then we split this distribution into blocks, like for instance 1 year blocks, and then we select the maximum if we of this block. So there's 2 approaches to select the extreme. One is the block maximum, and one is the peaks of a threshold. So first I explain the block maximum, which is the formula above. So we have our block of 1 year in a maybe 20 years or 1,000-year time series. And then we select the maximum in each year. That's our sample. The block maximum MN. Or the peaks of a threshold. So we select the threshold, and then we sample above all the points that fall above the threshold. The problem with this approach is that you have to also determine how high or low the threshold can be, because if it's too low, then you sample too many values, and then it's not anymore describing the tail distribution. And if you have the threshold too high, you sample too little, and you're almost at the block maximum. So for climate statistics, this is we have to carefully consider, because this threshold can also vary per region. So if you have a gridded model output and you look at different grid points, then this threshold, if you select it equally across all regions, that may lead to biases or errors. So ideally, you would need to determine your threshold for each location to find the best way to describe the tail. But for now, I'm focusing on the block maxima approach that is most often used in climate statistics because of this problem with the threshold determinants. But the block maxima has the limitation that if you only have a 20-year time series, then you are left with 20 values that you can fit your extreme value distribution to, and that's very little. So ideally you have 50 years, or you have more years to sample from if you do a block maximum approach. So then what you do, you fit to these block maxima, you fit the general extreme value distribution, which has 3 parameters: the location parameter, which basically characterizes the mean of the distribution; the scale parameter, which characterizes the width; and then we have the shape parameter that characterizes the tail behavior of the extreme values. And as you see, there are very differences between the 3 families that are combined in extreme value distribution. We have a bounded tail in the Weilbuch distribution, and we have a heavy tail behavior when you have a Frechet distribution. So the most extreme events you get if your extreme value distribution has a Frechet distribution. Okay, and so you're fitting this distribution to your block maxima, and then you have your parameters that characterize the distribution, and then you can inverse this distribution and come up with your return values. So basically, the return period is one divided by the probability of exceedance. So you can, with this method, you can extrapolate beyond the observed. So if you have a 20-year time series, of course, you can look by deterministic. You can say what was the return value of like the 20-year return value of the values in this time series. But if you want to look at the 50-year or 100-year return value, you can do that by extrapolating from the distribution you have determined from your sample. But you need to be cautious, because the further out you go in tail, and the further, basically, if you only have 20 years and you determine a 50-year return value, then the uncertainty gets larger, which you can see here. We fit it to the annual maximum temperature, the GEV, and you have here your return periods, that 1, 10, 100-year event, and the dots are the observations. And the further out you go in terms of the return period, the more uncertain your return value estimate, the return level estimate becomes. So the blue lines are the error, or the uncertainty around the return level estimate. So this is an instrument to extrapolate far out in the tail, but you need to know that the farther you go away from your sample size, the more uncertain becomes your return level estimate. And also, what is important to know is, when you think about events again, like a 100-year return or 100-year heat wave event, for instance, or 100-year temperature event, that you need to consider that an event is something specific to a location and to the definition in terms of what is the spatial extent and the temporal extent of this event, of the heat wave. And depending on that, your distribution can vary. And that's important when you want to do attribution studies. And in this paper here, it is described that the selection on how you describe or define your event, heat wave event, will determine what kind of distribution and also what kind of return level you get. For instance, for the 2003 event in Europe, depending on how they have 3 different methods, how you define your event in terms of time and space, gives you different distribution and also different return periods of this 2003 event. So there you also need to be careful.
Excuse me?
Yes.
Jana, may I add something? You even have to mention whether you are dealing with block extremes or threshold extremes when you mention these the return period and things, because these are 2 different types of extremes. So you should have to speak of a 100-year event for the block maxima of a certain block length.
Mm-hmm. Yeah, exactly. Yes. Yeah, thank you for this point. I try to keep here with the block maxima because you're going too deep into the statistics if we compare now the threshold and the block maxima approach. So this just to illustrate that there's certain caveats in the extreme value statistics that you need to be aware of when you want to apply it. And the other caveat is, as I already said, we rely on good data. And if you want to do this global, I mean, if you have a good station data, a long time series over Novi Sad or another place, then it's great. You can do extreme value statistics. But if you're going to a global scale, like we do in the IPCC report, we want to assess the global changes in extreme events, then we're running into a problem, because here you see a map of the global historical climatology network, and all these red dots are stations. When you see some areas are very well covered with stations and some are just blank. And then what do we fit here? We don't have the data, and often the stations also, they differ in the length of data time series they have. So it is difficult to do such a fit globally to observations. And also another problem is the changing climate. Even in the recent 10 to 20 years, even 30 years, the temperature time series has changed. So Manfred has showed you the consequences of having a trend in the data. And that is also a problem for fitting a general extreme value distribution, because you need to consider that your time series is not stationary but has a trend, and then we are in the non-stationary domain, and this makes it a little bit more difficult. But something else to consider, we call it covariates. You need to have a non-stationary DV with covariates, assuming trends or also other factors that could influence your time series. Like, for instance, the variability. I will come to that later. So the calculation of your return value depends on the quality of the observed records, the trends, and also, of course, the variable of interest. If you're looking at events, or you're looking at temperature, or you're looking at precipitation. So that's something to consider. And here I'm giving you an example of a non-stationary distribution versus a stationary. This is from a paper where I looked at the effect of climate or trend and atmospheric blocking, which is something that that's an atmospheric circulation situation, often called also blocking high, that causes cold waves in the winter over Europe, for instance, and hot heat waves in the summer, because you have these very persistent clear sky, sunny conditions, and in the winter that causes cold extremes because you have a lot of outgoing radiation and you have this inflow, especially in Europe, of Arctic air, and so it gets really cold. Anyway, so here I fitted basically the TV distribution block maxima to the era 40 reanalysis, and Carly has described what the reanalysis are. So we have 40 years, 40 values, for winter, and we have a stationary case, the solid line, which would be the distribution for minimum temperature over Europe, and then we have a blocking frequency as a covariate, and that gives you, and there's no blocking, so of course it's similar to the stationary distribution. But if we have blocking as a covariate, or if blocking occurs, then this whole distribution is shifted to the left, colder temperature, basically showing that when there is a blocking situation, then we can get a cold wave, or the colder temperatures. So this is showing you how non-stationary, how including some factors like trends or other covariates describing variability can affect your distribution, and with that also the 20-year return value. This is illustrated with these lines. For the stationary case, it would have been minus 20 degrees is the 20-year return value. But if you consider a covariate, then you have it's even colder. So that is just to keep in mind for the implications of having stationary versus non-stationary conditions. Okay, so but when you thinking about, I'm very interested in statistics, and so this is a good way that I can analyze my data using extreme value distribution. You should always first ask yourself, why do I want to fit an extreme value distribution? To have enough data? Is it really the right method to apply to get what I want to know? If for instance, if I want to extrapolate very far in the tail, and also consider non-stationarity, especially now in the context of climate change. We cannot assume that we have, even in the last 30, 50 years, stationary conditions. And don't make it too complicated, because the more covariates or the more or the less data you have, the more uncertain your estimate gets. And never fit to very short data sets, because then also your estimates become very uncertain. And don't go too far into detail if you don't have enough data. And I recommend this book. Manfred has also a book, but I started with this book when I started with extreme value analysis, and I thought it was a very good book with lots of interesting examples. But also Manfred's new book has also very many good examples. So both those books are probably recommendable if you're interested in extreme value statistics. Okay, now before I jump to the indices, to the other part of how to characterize or quantify, calculate extreme events, any questions about the extreme value distribution?
No, there aren't any questions in the chat. Maybe somebody wants to ask directly. Please turn on your microphone, sorry, and ask. Nothing so far. Maybe.
Sorry, can I ask something?
Yes, of course.
There is some noise in your voice when you're talking about the distribution, Weibull, Gumbel, and Frechet. Did you say that Frechet is the most common to the climate extremes, or I just misheard it?
No, Frechet is used a lot when we want to look at heavy tails. But yeah, so often the Gumbel is used in hydrology because they keep the parameter fixed at 0, the scale parameter at 0 to limit a little bit the uncertainty or the degrees of freedom.
Yes.
But if you want to look at heavy tail behavior, then Crochet is used.
Okay, okay. I just discovered it then. Okay, thank you so much.
Thank you.
Okay, good. Then I continue with the indices for climate extremes. So, as I said, there is a set of 27 temperature and precipitation extreme indices that was defined by this expert team on climate change detection and indices. A group that was formed or initiated by the World Meteorological Organization and the World Climate Research Program, WCRP, and CLIVA, and another organization. And this group set together to define these 27 indices as to describe indices that are globally valid and describe important characteristics of temperature and precipitation distribution, particularly focusing on extremes. And with this set of indices, they went into areas where there's usually either not much coverage in observational data, or in countries that don't release their observational data time series. So they held workshops in these areas, for instance, in Africa or Central America, and where they taught the researchers there to calculate these indices. And also Margaret will show you more about how to calculate these indices. But in these workshops that this ETCCDI team did, the researchers brought their own data and they calculated this in these indices, and then the ETCDI team was able to use the indices, not the original data, but the indices, and complement basically the data they already have, and come up with more more coverage across the globe for monitoring extreme indices or extreme events in temperature and precipitation. And these indices have also been widely used, have a long history to be used in the IPCC report. For instance, the FOST assessment report, you calculated indices based on CMIP3, the third generation of the coupled model intercomparison project, and then the special report on extremes in 2012 also used the indices based on CMIP3 models. And then in the fifth assessment report, I calculated all these indices based on CMIP5 model data, and that's what you find in the fifth assessment report. And the fifth assessment report was also special in that sense that for the first time we had a proper model evaluation of these indices, complementing the projections that we have had in previous reports. And here, these are a list of these indices, as you can find in the report. They're based on daily temperature, minimum and maximum daily minimum and maximum temperature, and precipitation, daily precipitation. And for instance, we have the warmest daily maximum, so the hottest day of the year, TXX, or the coldest day of the year, is the coldest daily minimum temperature in a year, TNN. We have, for instance, the wettest consecutive 5 days, which counts the precipitation that falls in 5 consecutive days. And then we take the maximum of these, and what are the maximum of precipitation falling in 5 days within a year. And that's often used as a flooding indicator because it characterizes the wettest condition in the year. And then also we have the consecutive dry days, which counts the numbers of days with precipitation below 1 millimeter. And that's often used as a meteorological drought indicator. Okay. The work of the ETCDI team, as I said, was important to monitor observed extreme events. And this website, you can find the historical data of these different 27 extreme indices. You can download the data, you can produce your own maps in time series for your location, for instance, and you can play around with the indices and the software on this website, which is especially, only for the observed temperature and precipitation indices. And the data was then used to also, it's shown in the fifth IPCC report, to show that globally the number of cold days is decreasing since the 1980s. So there's a strong declining trend in the number of cold days because temperatures are increasing, and with that also an increase since the 1980s in warm days globally. And you see that still, even for temperature indices, we have gray areas where we have no data, or not long enough data to produce these time series from 1950 to 2010, or the trends. Some areas only have very short time series or no time series at all. And for precipitation, this is even worse, with large areas over the globe where we don't have any data, so we cannot assess the trend. But for those data, for those areas where we have data, we can see that the very wet days are increasing, that the intensity of daily precipitation is increasing, and then there's areas in the world where we have a drying trend, for instance, in South Africa and Australia. And this is summarized in this figure, the main findings from observations that we can see in these indices, or in the assessment of the extremes, summarized in chapter 2 in the fifth assessment report. So the number of cold days and nights are decreasing, the number of hot days and nights are increasing globally. We have droughts, some areas the droughts are increasing, for instance, in the Mediterranean and West Africa, but in some areas the droughts are decreasing, like Central North America. And we have globally an increase in heavy precipitation events. And now we wanted to see if we can reproduce these trends also with the global models. So we used the observations, the indices, because that's much more complete data set of extreme events across the globe. We've also calculated the indices for the reanalysis, and you've learned what reanalysis are from Carly. It's a combination of a simulated observation into a global weather model, and we have the global climate models. And based on this, we can compare the indices from the different data sets and see how well the models are doing. And that's what we have done in this colorful carpet, which shows the root mean square error of a particular index, for instance, frost days here, for each of the models that were in the CMF5 ensemble on the bottom. And then we have each of the triangle shows one reanalysis, so the model compared to one of those reanalyses. And if you look, for instance, for this wettest consecutive 5 days, for instance, for the BSC model, then you see, for instance, for the NCEP reanalysis, blue, that means this model compares very well to the NCEP2 reanalysis. But if you look at the ERA interim, that is red. So this model compares not so well to the ERA interim reanalysis. What this figure told us at that time is that you cannot trust the reanalysis. The reanalysis are not the ground truth here when you compare to model analysis or observed extreme events, because the reanalysis, the products that they assimilate are not extremes. So they are just another model, so to say. So when you want to evaluate a model for your area, don't necessarily trust the reanalysis as the ground truth, but you need to compare with observations and also evaluate the reanalysis for your purpose if it's representing the extreme well. Okay, so but what we also find then, we compared here you see time series for the coldest nights, coldest days, for the models, and you have the CMIP5 ensemble, the newer model ensemble in red with the shading is the spread across the models. And then we have the reanalysis in green, and the HEDEX observation ClimDex data set is black. And you see that the observations, the models represent very well the trends that we see in cold nights, and cold days are decreasing, warm nights and warm days are increasing. So the trends are well reproduced by the models. But what we, when you look at other indices, which I don't show here now, but there's of course huge regional differences and also differences in the particular indicators, how well a model can represent a certain indicator. But overall, the trends are well simulated. We have, of course, there's a large range between the models, and the problem is with the underestimation of the extreme precipitation, because, as I said, there is a mismatch between, of course, observed point estimates of precipitation, which often is much more intense than what you can get in a model. So this, of course, you also see in the indices. But overall, this model evaluation told us that on the aggregated scale of indices, the models perform reasonably well to be confident in what we see also in the projection. So now I'm jumping to climate change. If there's any question about the observation, then I can answer now, but I can also continue.
Nothing is in the chat now.
Okay, then I continue.
Yes,
so
yes,
climate change. We heard from Carly that models can, of course, simulate future climate change based on assumptions how future emissions will evolve. And we have this curve here. We have the observed black, and then we have different temperature evolutions depending on the emission scenario. A low emission scenario, according to the Paris Agreement, would stay below 2 degrees, and so we have this blue scenario, and we have a high emission scenario. If we don't mitigate greenhouse gas emission, then we can end up in an 8-degree warmer world, for instance, relative to pre-industrial climate. And that, of course, leads to also a shift in the temperature, in the mean temperature, and then a change in the extremes, as I said. And as we go into the future, for the near term, this trend and what we see is dominated by uncertainties in the internal variability, for instance, circulation, modes of variability, that really affect the signal for the next decades. And then, of course, we have model spreads, because models are different. They have often they represent different processes differently well. I mean, and then the further we go in the future, this internal variability and the model spread become relatively less important compared to what pathway in terms of emission our society will choose. So in the long-term projection, 2100, it's really matters, are we really sticking with the Paris Agreement, or are we continuing as we do now with greenhouse gases? And not only this, these uncertainty in terms of model uncertainty and scenario uncertainty, but for the occurrence of climate extremes, also the processes are very important. The understanding of what are the conditions that lead to an extreme event. And these conditions are initial conditions, and also the large-scale drivers. For instance, the warming trend, of course, makes it more likely that we get hotter extremes, but also the feedbacks we see. So, for instance, for an extreme heat wave, the conditions need to be right to make a Russian heat wave from 2010, for instance, which was very significant in terms of length and intensity. So here we had, of course, the dynamic conditions. We had this atmospheric blocking condition, blocking high sitting over this area for a long time. We also had dry conditions from the spring, because the spring was pretty dry, so we had dry soils. And this kind of combination of atmospheric blocking and dry soils, that kind of encouraged or kind of provided very good conditions for a long and really hot heat wave. And also similar conditions, the interplay between different conditions lead to extreme rainfall events. And for us, I mean, scientists, it's important to understand the drivers and the initial condition feedback mechanisms of extreme events, because that helps us to potentially predict extreme events if we have a better understanding what conditions have to be right to produce a very extreme event. Okay, and this is, of course, we have different time horizons we can look at extreme events. The prediction part is often, we have subseasonal to seasonal forecasts, which could be used, but then we have also decadal predictions, and then we have these long-term forced boundary conditions where the scenario, the pathway, the emission pathway plays a big role. I'm focusing here very much on the long-term climate change prediction or projections. I'm not talking about weather or seasonal forecast or decadal prediction. So future changes in the hottest days. So here we see the warmest daily max. So this is the warmest day in a year, and how it changes over time, globally averaged for the historical black line till 2005, and then the three scenarios: the high emission, the low emissions, and a medium emission scenario. And you see that the warmest daily max can increase up to 6 or 7 degrees globally. And this translates to the last averaged over the last 20 years. Here in this time series, you see this global pattern of the warmest day of the year, and you see that mostly the continents, inner continents, are warming a lot for the end of the century. The same we can do for the coldest day of the year, and here we see even stronger increase, up to 8 or 9 degrees in the highest emission scenario. And this translates, if you look at the last 20 years, into such a global pattern where the strongest increase in the temperature of the coldest nights will be experienced in the northern hemisphere, northern latitudes, due to this sea ice retreat in the Arctic and other land surface feedbacks, for instance, also the permafrost thaw. So just to make you aware that there's differences in, if you look at minimum temperatures, cold extremes or hot extremes, in the pattern you see globally. So for us in the Central Europe or Northern Europe, that means that we see much stronger warming in the winters than we see in the summer. And now coming back to the combination of indices with the extreme value statistics. So since these are the coldest day of the year or the warmest day of the year, this is basically a black block. This index is a block maximum. So you can theoretically or in practice fit a GV to that, and that's also done. And this is also a figure from the HIFT assessment report, where the 20-year return value is calculated based on the GeV distribution for the maximum, the hottest day of the year and the coldest day of the year, and for a low emission scenario on the top and a high emission scenario in the bottom. And you see also here these patterns that I described. If you focus on the lower panel, we have the strongest warming for the minimum temperatures in the north, the return values, and a more continental warming for the hottest days of the year. But so this is a general global map, but that's not really how we perceive heat. When we think about, heat extremes, we're thinking about heat waves. So that's why we also need to think about other indicators that describe heat events, and this is heat wave indicators. There are plenty of heat wave indicators out there. We have also developed one. It's called the heat wave magnitude index, and this has certain advantages towards other indicators because it can characterize really the event in itself. And we showed that in this paper, where we showed that with the indicator we can observe heat waves that had a high impact. For instance, like the August 2003 heat wave in France, Central Europe, or the 2010 heat wave in Russia. And this indicator is basically what we do is we have our daily temperature series of daily maximum temperatures, and we look at the 90% threshold, and we select the days where the temperature is above the 90% threshold for a particular grid point or location. And then this condition has to last for at least 3 days. So it's only heat wave if we are above the threshold for more than 3 days. And then we have these different events that classify as a heat wave. And then we look at the longest and the hottest. So that this indicator combines both the information about the length and the information about the intensity. And then we have this heat wave magnitude index that describes both characteristics for this hottest or the most intense heat wave for the time series. And that we did globally for different, of course, we captured different events. For instance, the Russian heat wave, the Paris heat wave, and in 1980 we also had a heat wave in North America. And we can look at how these events in the future becoming more likely. For instance, here the Russian heat wave, which was an extremely intense heat wave compared to the reanalysis and the years before. And then if we look in the time ahead till the end of the 21st century, for the strongest emission scenario, you see that by the middle of this century, this heat wave becomes kind of occurs more often, and by the end of the century, we have many of those similar events occurring. And a heat wave like the 2003 heat wave even occurs more often in the starting from 2030 already, and becoming much more intense in the future. So this is a general trend in these heat waves that we have observed becoming more often and more intense in the future. And also here to this heat wave magnitude indicator, we can fit a GeV, because we can also extract the hottest heat wave event from a 10-year decade. Here we used long simulations with more than 1,000 years, and we selected the hottest heat wave in a decade, and we fitted the GeV to it. And here we looked at the distribution, like is it a Gumbel distribution or Frechet distribution, and you see that Frechet is often preferred, so the heavy tail distribution is the best fit to this to the distribution of heat waves. And then we could, for each grid point here, we take one grid point as example, we can calculate the return period. So the 10-year return period, or a 200 or a 500-year return period. And as I said, it's a 1,000-year record. So we are still pretty good by taking a 500-year return value. And for this location in Central Africa, the 500-year return value would have been a heat wave magnitude of about 25. And if you look at the future projections, this kind of intense heat wave with 25 magnitude is now a 12-year event. So it's much more frequent. And the 500-year heat wave return period is now actually would be an event much more intense, like with 60 heat wave magnitude index scale. So this just characterizes how climate change will change your statistics and the return values of a specific event. And this is just shows that the difference between 1.5 degree warming and 2 degree warming, the probability and return level of a heat wave with the 500-year return period. And you see for two different models that even for only half a degree between 1.5 and 2 degree warming, there's much more intense heat waves to be seen and spreading much further north. But also, I mean, we cannot only stay with global models. We want to go more regional. We want to learn more how heat waves occur, for instance, in Europe. So we're using more the regional climate models that are available through the coordinated regional climate downscale, coordinated regional downscaling experiments, CORDEX, to look into near-term changes in heat waves to better be prepared maybe for events like if they occur again, like the 2010 Russian heat wave. And here we have different regional models. All the panels show, each panel shows one regional model combined with the global model. And you can see that one global model can drive different regional models. Like for instance, the CNRM is a global model that is used to drive the RCA regional model, and here the same global model is driving the CCLM regional climate model. And we're looking into the high emission scenario for the next 30 years, or basically now it's the next 20 years, but for this 30-year period in the projection 2011 to 30. And we're looking at the hottest event that in these 30 years stimulated by such by each of the regional climate model. And what you can see is that a heat wave of the magnitude of the Russian heat wave can occur within these 30 years at any time and in any place in Europe. So, and also, for instance, 3 models also show such a heat wave could appear around the area of Serbia, for instance, as well. So we need to consider that here in the next 2 decades, we have an increased probability of extreme heat waves, but where and when they occur, we don't know, of course. The changes are masked or amplified by internal variability. As I said, in the near term, internal variability plays a big role, meaning where does an atmospheric blocking event, for instance, occur, and where is it basically further fueled by dry surface conditions to create the perfect conditions for the mega heat wave. And that we cannot, of course, foresee in these projections, but we hope by our process understanding, we can make progress in predicting better these heat waves. And here I'm showing the heat waves and atmospheric blocking relationship a little bit better to show you the effect of internal variability that determines also the probability of these events to occur in the next decades, with kind of mask or kind of makes it difficult for us to say where and when exactly the heat wave occurs. But we have the heat wave magnitude index, for instance, here for the 2010 heat wave. And then we had at the same time this high pressure anomaly sitting over the same area, which is I call atmospheric blocking. And we have looked at many simulations, and here we have ensemble simulation of one model with 50 ensemble members, and we can see that where this block sits, basically here the square that is moving is the high pressure system, and where it sits we have anomalously warm temperature underneath. So so basically the location of the block determines where we get the heat wave, and also not only the location but how long it lasts. And this is basically the difficulty of models these days to simulate the long-lasting blocking conditions, or also predict how long it lasts. Okay, and in this we showed that there is a strong relationship between the blocking conditions and the heat waves. We picked two heat waves, the 2003 heat wave and the 2010 heat wave, and these are the observations, or not observation, these are the reanalysis, the events in the reanalysis, the heat wave magnitude index, and the days, the block days, when the atmospheric blocking or the high pressure system occurred. And there's there's a relationship between the length of the heat wave or the heat wave magnitude, for instance, for 2003 heat wave or the 2010 heat wave, and the block days. And we also see that in the large model ensemble here, the plots, the blue dots all indicate one ensemble member of this model, and they nicely cloud basically the reanalysis results. And we can see that for other models as well, like the CAN-ESM, we also see this relationship between heat wave magnitude and the atmospheric blocking days. And especially if we look at this more higher resolution model, we can see that the 2003 event is something that actually is it was something extreme for the reanalysis or what we have observed so far, but in the model space there could be much more intense events than 2003. So 2003 wasn't actually what is the most intense, but for the 2010 event you can see that only one ensemble member really captured such an extreme event. So it's possible also in the model world. It's nothing that the models cannot produce, but it was still in the observed and model world one of a very, very extreme event you see at the right corner. So that also gives us confidence that having enough large ensemble, having enough model simulations or ensemble members, we can capture extreme conditions. But if you have only one ensemble member or too few models, we might miss that extreme event. Okay, now I'm stopping with temperature and come to the remaining part of my presentation on extreme precipitation. So I have 15 minutes. Any questions?
There aren't any questions in the chat. So.
Good, then I continue. Future exchanges in extreme precipitation. Also here we use the indices. The wettest consecutive 5-day indicator. We see globally averaged, we have about a 20% increase in these wettest 5 days conditions for the high emission scenario, and only a 5% in the low emission scenario. The high emission scenario averaged over the last 20 years of this decade, this century, translates in this global pattern, where we see in most of the land areas, we find an increase in these wettest consecutive 5 days conditions. Only a few areas like Southern Africa and the Mediterranean experience a drying or not, and not so strong increase in the wettest conditions. And this is matched by this maximum consecutive dry days map, so the trend in meteorological drought conditions, which are strongest in their increase in the Mediterranean, in Southern Africa, and also in Australia. South America. So we have areas where it's, I mean, also where the drought conditions are becoming less, which are areas where also the extreme wet condition increase more. So the northern latitudes will experience much more wet extremes in the future. But this is very coarse. So for floods or for city flooding, for regional planning, this is too coarse. So especially for precipitation, which is more localized events, we need to go higher resolve. So we go from global climate models to regional climate models. And here we basically resolve the process or the characteristics of precipitation in a much higher way. We go, for instance, from 100 by 100 square kilometer, 100 by 100 kilometer square to 50 by 50, or even 11 by 11, or 10 kilometer grid point size. We have the Eurocortex simulations, but this is still not enough to really resolve the reality. So a grid box is very difficult to capture the clouds, for instance. So often clouds are parameterized, even in regional climate models. And this transition from global to regional model and even higher resolutions to these days is of course accommodated by having increased computer power. And even today, some of the global models are higher resolved than some of the regional climate models. But yeah, so as I said, we need these high resolution to resolve convective storms, for instance, that are very localized events over very short time, compared to these large scale systems that we can capture with the 5-day consecutive maximum precipitation index that I explained before. And these more convective events are resolved in weather models. So they resolve convection, and of course we see them also in the radar. And so now to come more closer to these weather models and to the what we see in radar observation, for instance, in the recent decade there were strong development in convection permitting models, regional models that are like down to a 1 kilometer or 3 kilometer resolution that don't parameterize convection, but they really model the convection. And here you see the difference that in mountains and or areas with complex topography, we have a much higher resolution and get much higher precipitation intensities than we could ever get with the coarser resolved model. So this is very important for simulating heavy rainfall events. And as I said, even on a global scale, we are at the level that we can have very fine scale simulations that can resolve tropical cyclones. You can watch this YouTube video later. I don't click on the link, but because otherwise I may screw up this presentation. So, but you see how these tropical cyclones move over the ocean and hitting land. But this, of course, this kind of very high resolve simulations comes to the expense that we cannot run 100 years of projection. So we can simulate that for a year maybe at this high resolution. That basically comes to the expense of making projections versus being high resolved. That is also a problem, is also the data availability for the model evaluation. Do we have sub-daily scale precipitation observations to evaluate our convection permitting models? And how do we detect trends if we only have a short time series for the models, for instance? And then with the high resolution, it also comes to higher computational expenses. And if we cannot simulate longer time series, we may fall short of representing natural variability, trends, and it's difficult to assess uncertainty if we don't have a multimodal ensemble, for instance, if we don't have a longer time series. And also, as I said, these indices for extremes, they were based on daily temperature or daily precipitation. And if we go for even higher result on sub-daily scales, we need to think about new metrics and indices for extreme events. So we can also compare maybe across regions to assess trends in these high resolution extremes. And just to point out what it makes in terms of difference to look at regional projections or simulations of extremes and basically more larger temporal and spatial aggregated extremes versus going very, very high results. So this is a paper by a colleague here at Cicero running convection permitting model simulations. And here he did it for southern Norway. You see this tip of Norway, where you see a trend in the end of century under high emission scenario go towards more drier mean summer precipitation. So Norway becomes drier in the summer according to this simulation. But then if you look at the 1 day maximum precipitation falling in 1 day, you see already that the 1 day precipitation becomes more intense. It becomes wetter. And if you go to 1 hour or even 10-minute precipitation, then you see a complete different picture. So the short-term, very intense rainfall events in summer, usually with these thunderstorm events that happen there and here in a very small location, they become more intense compared to a more overall drying trend in the region. And in this paper, you also find the region Albania that he modeled, and the southern tip of Serbia is there. It's not full Serbia, but you can see that also here in Serbia, we have a more drying trend in most of the areas. We have also a wet spot here for the mean summer precipitation. And the further down you come to the short-term, very localized events, you see a wettening trend, and especially in this area, which is already indicated as wet in the mean summer precipitation. So these are very important take-home messages. It's like the very aggregated precipitation statistic may hide the changes that can occur on very short-term or very localized scales. So high-resolution simulations are important when you look at future precipitation extremes. And not only like the high versus low or aggregated precipitation statistics, but also for precipitation, there's two characteristics that make up these events. It's the frequency and intensity. And Gunnar Möhre, also a colleague here at Cicero, has looked at the difference in changes in frequency and intensity for Europe, and he has shown how in an observational data set, EOPS, both the frequency and intensity of precipitation events are increasing, but in the global models, they show also this increase, but in the much, for instance, for the intensity, it's much less intense because of the scale, the mismatch between observations and global aggregated grid boxes. And this basically brings me to the end of the extremes in the physical sense. Just very quickly, not to forget that weather in climate extremes, we have to see them in the context also of impacts. And there's much in the media about how heat waves becoming more frequent, and they're due to climate change. And we are seeing in the media a lot of the impacts for forest fires. We see the droughts. And this brings me back to this risk framing of the IPCC, where we need to see the physical changes together with the socioeconomic impacts that climate extremes have, which is assessed. The impacts are assessed in the Working Group 2 report and in this special report on climate extremes. And important concept of risk is that in this report they have specified 5 key reasons for concerns, and among those are due to climate change, and among those are extreme weather events. And when you look at this curve for the high emission scenario, where we go up to 5-7 degrees global warming, versus the low emission scenario, 2 degrees, then for extreme events, even if we stay below 2 degrees, we are already in the phase of between moderate and high risk. So even with the climate change that we already have caused by the emissions that we already produced, we are in a moderate to high risk from climate extremes. So we need to adapt to the climate change we already experience. And especially in this global warming of 1.5 degrees, special report by the IPCC coming out, it came out in 2015. It showed for different sectors that it makes a difference if we are warming, if we have a global warming between 1.5 or 2 degrees. Because at the 1.5 degree level, we are still at moderate risk and transitioning to high risk when we approach 2 degrees for fluvial flooding, for crop yields, for heat-related mobility, tourism. So it really matters if half degree warming, if we mitigate or not, if we start mitigating now. And in the new IPCC 6th assessment report, we choose to not scatter the assessment of extreme events in different chapters. We have it in one chapter, chapter 11, and we have a special chapter 12, where I'm a lead author, and Carly was the chapter scientist on climate change information for region impact and for risk assessment. And here we're trying to provide an assessment of climatic impact drivers that are relevant for this risk assessment in Working Group 2. And if you are interested in more aspects of climate extremes and their implications for impact and risk assessment, I recommend you this book, which goes through the changes of climate extremes, but also applications of in different sectors where impacts of climate extremes with different methods were analyzed, to the, for instance, social science aspects of climate extremes, triggering conflicts or security issues, up to what it means to mitigate or adapt to climate extremes and transforming the society. And the other papers that are listed here are further reading that support what I discussed in my presentation.